Hello. Oh, well done. You've got to the end of week 2. So what you've managed to do this week is really capture the essence of functional programming in Erlang. You've seen lots of examples of programming with lists, and that's just a great thing to look at because they embody all the things that we do in functional programming. You've seen recursion, you've seen the way we deal with structures, and you've seen that, and we'll build on this in future weeks, you've seen that certain patterns emerge for computation. Doing something to every member of a list, selecting elements of a list, combining elements of a list, and things of that sort. And we'll come back to that, and we'll see that higher order functions have a very special role to play there. One thing I wanted to say generally, just about how the MOOC is going, is do feel free to comment on each other's work. One of the things that we'll do next week is get you formally to do that by using the sort of structures that FutureLearn set up to support that. But what I'd like you to do, even just in the comments, when you post a solution in a gist, once you've posted your solution, why not look at somebody else's and see, first of all, you can compare what you've done with theirs, but also if you see something useful to say to them, just say it. So we'd encourage you to learn. Learning isn't all about talking to the people in the middle of the wheel. Talking around the edge of the wheel is just as valuable. You learn a lot by interacting that way. And I'd really like to encourage you to do that. I'd also like to thank again colleagues from the Erlang Ecosystem Foundation who are commenting on code. I'm really grateful for that. But do feel free, you do join in yourselves as well. The other thing I wanted to say, and I'm going to turn to the using the editor here, is just to encourage you to use pattern matching. Pattern matching allows us to do a number of different things in Erlang. It allows us to test for equality. So that's really helpful. We don't have to write an explicit equality test because we can use repeated variables. But we can also do other things. We can, and taken together, these makes it a very powerful facility. We can distinguish between cases. We can say, is this list empty? Or is this list non-empty? But we can also, once we distinguish between cases, we can delve down inside structures. We can extract elements or components from structures. And I thought it was worth just running through an example just to bring that element home. So if suppose we have a list of pairs like this, I don't know, we have an atom and a number, and we have something like this: foo3 bar 27, foo5, and what we want to do is look up a value in there. So what we might do there is our lookup function could do one of two things. It could find the first value. So if we call that list, let's call it list, then if we said lookup in list the element foo, we'd get the answer. Let's just say it's equal to 3. Or alternatively, we could get the answer, well, it's a list of results. And it would give us the list 3, 5. Because it would find all the things that correspond to foo in the list. Let's go for the second option here. So let's define a lookup function that does that. Well, whatever we look up, let's say the atom A, in the list, in an empty list, the answer is going to be, oh, nothing corresponds to it. So the answer there is empty. On the other hand, suppose we look up in a non-empty list. Now, we could say non-empty list looks in general like x cons x's. It has the element x at the beginning and its tail is x's. So if we were thinking of the example here, foo3 would be the head and the list with bar 27 and foo5 would be the tail. But we know more information about this head than just that it's an x. We know it's actually a pair of things. It's an atom and a value. Now, depending on whether that atom equals, the atom B equals the atom A, we do two different things. So let's actually use the fact we can use repeated variables here to say, oh, we're looking at the atom A in this list. Well, we found a corresponding value V. So that must be the first answer of the result. But there'll be other things in the result potentially, and those would be the things that we get up by looking up A in x's. So there we've got a second. There we've got our case. And then we have a final case when we look up, and I'm going to just copy this for ease of use. I'm going to copy that line. And then what we're doing here is we'll have a case where the two things are not equal. And then what we do is simply look up A in the tail. Now, we're getting some warnings here. We don't use the value of the variable there, so we could put an underscore there. And in fact, we don't use the value of the of either the B or the V here. So in fact, we could just say whatever the first pair is, if it doesn't match A comma V, there is our answer. And you can see, and let's just line this up so we get our arrows in a line. And you can see that I've used the power of pattern matching to distinguish cases. Here we have an empty list. Here we have a non-empty list. To look inside a list. So here we're saying this is a list whose first element is a pair A comma V and whose remainder is x's. And so that will match, if we match that with our example list, A will be foo, V will be 3, and x's will be this whole list here. And then once we know the head isn't a matching pair, we're not interested in the head, we're just interested in the tail. So in fact, one other thing you might add to this is that we can be very clear about the elements, components we're not interested in. And there we use an underscore or an underscore variable. So just looking at those patterns tells us an awful lot about what the function does. Okay, I'm going to stop for now, but that gives you just one more piece of, one more example of how pattern matching is of value.